history math. So are there any questions? Has anybody else tried the 1-1 homework out yet? If you haven't, I don't really understand you. You need to get into the homework so you can come with questions. Yes? Yes?
I was wondering if you could go over, or if you could explain problem 35.
35. Interesting. There we go. Let's see if I can. 35. Well, 35 says, so for example, look at 33 real quick. By the way, my book I actually got it, actually paid for it myself, but so somebody else marked 33. The angle here, find the measure of the smaller angle, so that would be this angle. Just look at 33 just to start. I know the question is 35. But how would you figure out 33? How would you figure out that angle?
I did 5/12 of 360.
Yeah, so so if it was right here, it would be 0. Here would be 1/12 of the whole way around, correct? 315 gets a little bit more interesting, but you can kind of draw it and kind of go from there, right? How do I want to say this? Let's see, think. Because if it's given to you drawn already, that's a little bit easier, right? You guys all with me? Okay. What gets a little tricky is the hour hand doesn't just stay on there, so I'm really not exactly certain how precise they necessarily want you to be. Because this example here, let's look at this one real quick. Become a thing. Okay, there we go. So it's not just, how do I want to say this? It's not, so it's 1, 2, 3, 4, and then a bit more, correct? You guys see that?
Yeah.
So it's not 4/12, it's because it's a little bit more. It's not 5/12 because this sucker's not pointing right at the 2. Are you guys all with me so far?
Yeah.
So this is, okay, let's see if you guys are cool with this. What's most important right now is that you can visually identify about what an angle is. And if I ask you to draw an angle, you can kind of give me an estimate without a protractor, for example, right? You guys all with me? That's what I really want you to be able to do. This specific problem has a little bit extra going for it. Let me see if you guys understand how clocks work, because we don't really think about it that much, and most of you guys are like, I don't look at that shit, I'll just look at a digital clock, man, what the hell? But, how far between the 1 and the 2 is the hour hand at the moment?
3/4.
Yeah, exactly, because I'm 3/4 of the way through the hour. You guys with me? So it's not 1, 2, 3, 4/12 of 360. Why would I do of 360? Because the whole clock would represent 360 degrees, correct? So the first one, like somebody said, it would be 1, 2, 3, 4, 5/12 of 360. And you just do that problem. That'll say how many degrees you've gone through. Are you with me? This one's a little bit harder because this is not lined right up on a number, but it's 1, 2, 3, 4, and, like you just said, 4 and 3/4 time 12ths of 360. So what would that look like if I wrote it down? We'll write it down and find out, Jeff. Oh yeah. Paper. My kingdom for a piece of paper. So if I wrote this down, 4 3/4 twelfths. Does that look exciting? Time of 360. Why the shit am I doing that? Does everybody understand why this first problem would be 5/12 of 360? Because 12/12 would be all the way around. That would be 360 degrees. We've gone 5/12 of the way around. More directly, these are 1, 2, 3, 4, 5 hours apart. 5 little tick marks apart. Okay. Out of 12. So here we've gone 4 3/4 twelfths of 360 degrees. Well, does 12 go to 360?
Yeah.
Yes. How many times?
20.
30. So now it's 4 3/4 times 30, right? And then you can, if you want to, you can make this in an improper fraction, right? So let's see, it'd be 16, that'd be 19 fourths times 30. Does this reduce? And actually, I don't think the problem said you had to give the answer in fractional form. You can just throw that sucker in the calculator, to be honest. You didn't really ask for a fractional answer, right? You guys with me? But just out of curiosity, this would be 2, 15. 19 times 15 is something. Is it 285? Somebody help me out, is that right? 19 times 15? Out of curiosity.
Yeah, 285.
Yay, okay. And then that's just gonna be 142.5, is that right? So 142.5 degrees. Now, the actual question was about number 35, but if you understand what I just did for number 34, you can do the exact same thing for number 35. 3:15. How far between the 3 and the 4 is the hour hand?
1/4.
1/4, because it's 15 is 1/4 of an hour, right? Are you guys all with me? Okay, I love you guys. Some of you guys out there are like, you old man with your clocks. Sorry. Is that better? Is that all right? That is definitely a freaky, no?
I kind of forget it.
So this one. Do you agree? Well, first off, this one. Does anyone not quite get this one? How far apart are these two? Aren't they 5? Out of how much for the whole circle? 12. So it's 5/12 of the way around the whole circle. The whole circle would be 360 degrees. Therefore, it's 5/12 of 360.
Okay.
5/12 times 360. That one's nice because the hour hand is perfectly on a number. This one sucks, and so does this one, because the hour hand would not be perfectly on a number. Why was this one 3/4 of the way between these two? Because how far through the hour am I? 3/4 of the way through the hour, right? What's left? Isn't it a quarter of an hour before 2? Isn't this a quarter before 2?
Yeah.
So didn't we go 3/4 of the way around already? So this would be 3/4 of the way. So 4 3/4. 3:15, I would draw the clock, right? 3:15 will be 3 and 15 is how much of an hour? 15 minutes. It's 1/4. So it'll be just 3 and 1/4. Okay, that one is clock math. A little bit out of nowhere, but yes.
So could you just do 1/48 times 360 to get the answer?
1/48?
Yeah, because if you're a quarter away of the hour of the between times, like that's 1/12 divided by 4, which is just 1/48.
Oh, 1/48.
Yeah.
I see. But it's also the 3 though.
The 3 is
And it's not 1/48 because let me see. Let me make sure I see what you're saying. It's not 1/4 of 1/12. It sort of is. You could set it up to use that, but it would take a little more work. It's just a lot easier just to go 3 and 1/4.
like as the answer.
No, that's the first step.
Oh yeah. Yeah.
So we've gotten 3 1/4 of 360,
Mm-hmm.
of 3 1/4 twelfths of 360. Yeah.
So I got the right answer, but in a totally different way. I wanna
Cool,
make sure.
tell me. Because that's the first way I thought of it.
Yeah, so between every number, there's 30 degrees,
I love it.
right?
So you can break down 1/12 of 360 is
Yeah.
30.
The minute hand is gonna be on the 30 exactly. Right?
Oh, for this one? Okay.
Yeah.
Yeah.
The hour hand is gonna be a quarter of the way through that. So 30 divided by a quarter, 7.5.
30 divided by a quarter. Yeah, okay, beautiful. And that's, I think, what you're saying.
Yeah.
Because I needed to draw the clock, otherwise I didn't even really think about where things would be. So at 3:15, this is, let me see, oh, here we go. 12, 1, 2, 3. So at 3:15, this is pointing directly at 3, because that's the minute hand, and the hour hand will be pointing about 1/4 of the way between, yeah. So that's what you mean, now I'm with you, okay. I love it, so every step is 30 degrees. And so then from there you can kind of build, and you can cut that down. I love it, both ways work.
What I didn't understand is, so we can obviously check some of the answers in the back of the book, right?
Sure.
This one is one of them. It gave the answer not in that form, not 7.5 degrees. It gave it as 7 degrees and 30 minutes.
Oh, okay.
I don't understand why it did that, because it didn't tell you to do that.
It didn't tell you to do that, no. So
Yeah.
I would argue that.
Okay, either way,
Yeah,
either
yeah.
one, okay.
There will be times, you all know this in math class, when the back of the book gives you one representation and you wrote it a different way because you solved the problem a different way. No worries. If it doesn't say specifically what form they want the answer in, there's a few other ways to write the answer. You're good. I like it. So what I really love about math is just you'll get a way you think of it immediately, and then there's other ways somebody else could think of it.
Yeah,
Right?
the way you did it was crazy. And I hadn't even thought about that.
Oh, okay.
You know.
Oh, I'm sorry.
no, it was much
The
more
way I did it
complex.
was the most direct way to do it.
Yeah, it makes
Uh,
sense though. When
yeah.
you said it.
Yeah.
I wouldn't have thought of
And so this is a really key thing. Whenever I'm doing a problem in here, if you have a different way of looking at it, feel free. I do try to show multiple ways to do a problem. This one I was just trying to do quickly as the first thing I thought of.
Yeah.
So I'm wide open to somebody else going, that's not the way I did it. Because you sat with it for longer than I just did, right?
Yeah.
So I'm cool with that. I love that idea of breaking it down to 30 each. That's easy. That's nice. Kick ass. I like it. So definitely feel free to speak up. Don't just go, well, this is the way this guy must want me to do it. No, it's just the way I thought about it.
So, as honestly, I got 12 over 12 times 360
For which one?
for 35. And
Why?
because I didn't think of it. I thought that 3 was on 15 through 15. I
Yeah.
did it super quick. Oh my goodness.
Oh, so you should have gotten 0 actually then. If you thought they were lined up with each other,
Yeah.
then you should have gotten 0. Because they would have been lined up. There's 0 degrees separating them, right?
Hmm.
If I rolled the time back, isn't this getting smaller in the angle?
Yeah.
So if they're right on top of each other, that's 0.
Hmm.
Yeah, what's a 0 degree angle? How do you represent that? Flat. Right? Yes.
If you say leave your answer in exact form, do you want us to leave it in the minutes, seconds, degrees form, or do you want us to leave it in decimal form?
Some decimals are exact, some aren't.
Okay.
Pi. What's pi? I love you guys.
1/4 plus a million other numbers.
Exactly. So what's the exact way to say pi? Pi.
Pi.
Anything else, any decimal you give me is not exact. You guys understand? Because 3.141596, this is as far as I know. Doesn't it go more? So is that exact? No. I love it. If the answer is 2.5, 2.5, that's exact still because there's no more decimals. Does that make sense?
Yeah.
So I think the problems we did, the decimals end. That's still an exact answer. Okay. Yes.
I just wanted to just clarify something because so whenever what was it? for problem 34, like when the little hand was between 1 and 2, you would say 3/4, right? Because
Yeah, it's 3/4 of the way through. Now, another way to do it, like somebody just said, was each step is 1/12 of the whole way around. So each step is 30 degrees. So you kind of go 30, 60, 90, 120. And then you have to go plus 3/4 of 30. And just to point out, 4 times 30 is 120. And then I still have 3/4 of 30 more to go. So the math we did is the same. Do you see what I'm saying? It's the same math. This just does it all at once, whereas you kind of broke it down, which is beautiful. Okay. Neither of those were the right way. They're both valid. They both end up being the same math. Okay, maybe. Is that all right?
it makes much more sense.
Now, I'm not going to spend any more time on this because this is not like a major idea. This clock trig is not a huge part. It's just a little tiny side note problem. Okay. Anything else from homework stuff? Yes.
Number 60.
60?
Yeah.
Here we go.
My main problem was I noticed when I plugged the 18 seconds into a calculator, it gave me 0.5 instead of 0.3.
18 divided by 36.
Yeah, so you gotta be careful. A minute is how much of a degree?
60.
And how many minutes are up in this problem? Which part of that is minutes? 42, good. So it'll be 42 out of 60, right? A second is 1/60th of a minute. So a second is what part of an hour, or what part of a degree in this case? 1 over 3600, right? 1/60th of 160. So if I ask you how many seconds are in an hour, 3600. 60 seconds every minute, 60 minutes every hour, 60 times 60. So every second is 1 over 3,600th of a degree. So I would do 38 plus 42 over 60 plus 18 over 3,600. Not 18 over, I think you must have done 36 or something. You must have gotten 0.005 or something, because that's,
Oh no, I just did 18 over 60.
oh, 18 over 60, okay. Do you understand now it's 3,600? Okay. You guys all good? So a degree is 1 of a degree. A minute is 1/60th of a degree. And a second is 1/3600th of a degree. Just like hours, minutes, seconds are in our normal everyday life. Okay, maybe. Maybe not. Okay. Okay. Yes.
Could we also go over 110? Because I was confused a little on
Let's see, 110. Which two of the following are not coterminal? Okay, with, oh, where's it? Wow, you were zoomed in. So this one. So R degrees. So just, they don't tell me, they're like 10 degrees, right? Can you give me, have we talked about coterminal stuff? I'm pretty sure we did.
Yeah, we did.
Yes.
Right, isn't it just adding or subtracting a rotation? So what's coterminal with 80 would be 440, for example. You guys with me? Because if I start at 80 degrees and I go a full rotation, isn't that ending up in the same place? Coterminal ends in the same place. Coterminal, you gotta love that shit. All right. So they're just saying, I'm not gonna tell you what number it is, but what always gives me a coterminal angle? Well, obviously, one answer, and there's a few, is what we just did. If I give you an angle, how can you always find another coterminal angle? You just add,
Plus or minus 360.
well, you add 360. Or you subtract 360. So what two answers work up here? A and B. What about C?
Yeah. Yeah.
All right, let's wait. 10 degrees. 10 degrees. If you add 360, you get 370, yes? If you subtract 360 from 10, what do you get?
Negative.
Negative 350. You guys with me? So does 360 minus 10 work? Do you get 370 or negative 350? Nope. So that doesn't work. What do you do to get to a coterminal angle? If you're given an angle, you either add a full rotation or more than that, right? Or you subtract a full rotation, right? So that 360 minus r doesn't work. Yes?
So by that concept, then wouldn't A also not work as well?
Why?
360 degrees plus r degrees?
So if I start at an angle,
Because if r degrees is equal to 10,
say 10, say I start at 10 degrees. If I add 360, isn't that just a full rotation?
so
If I add or subtract any number of full rotations, I'll end up in the same place.
okay.
So really, I'm just saying, if you pick an arbitrary direction to look, and then you spin one way a full turn, or you spin the other way the full turn, you're going to end up looking the same way. That's what A and B say. Where do you go? There. You guys kind of with me? Yes?
Doesn't C also represent negative r plus 360, which is also coterminal?
It would be coterminal with negative R. It's not coterminal with R. This would be coterminal with negative R. And you just said why? Isn't this negative R plus 360?
Mm-hmm.
Isn't that coterminal with negative R degrees?
Yeah.
Is 10 degrees coterminal with negative 10 degrees? Are they coterminal? Nope. So that's, you just gave a beautiful explanation as to why that's not an answer. Is that coterminal with R? No. It's coterminal with negative R.
So how is D coterminal?
I didn't say it was.
Yeah.
So far we got A and B.
Which two in the following?
Yeah.
Which
Yeah.
two?
Which two? Oh, so are you asking why this doesn't, you think this should work?
No,
Okay.
because I was thinking with that one, it doesn't go in a full rotation.
Beautiful. So it would never come back to the right place. It would be exactly the opposite, right? It'd be pointing the exact opposite direction, yes? That's like just going a half rotation. I'm now looking the exact opposite direction.
yeah.
So I'm not coterminal. I love it. Are you guys with me? So how do you get coterminal? You add rotations or you subtract rotations? Well, how much is a rotation? 360. So you're going to add any number of 360s or you can subtract. So is 3610 coterminal with 10? 3610 degrees is a coterminal with 10 degrees. Yeah, I added 10 rotations. What's 10 rotations? How many degrees is 10 rotations? 3600. So if I start at 10 and I add 3600, I just rotated 10 times, which I'm not going to do right now because then I'll fall over. I will fail, walk in a straight line, and I might get fired. I won't do it. Yes?
I had a question about a separate question.
Sure. Is everybody good with that one? The only way to really directly get a coterminal angle is to add or subtract full rotations. Add or subtract 360 degrees. Yeah.
I had a question about 100. I just don't understand it. I'm pretty sure we went over it, but that was something I didn't really like.
Well, this is. So give two positive and two negative angles that are coterminal. Oh, so just like, and by the way, the word quadrantal, you're gonna look that shit.
Yeah,
up. Oh, and you're not really recording anything I'm talking about, are you? Poor little dude. When we draw XY plane, how many quadrants do we? And of course, the word quad gives it away. It's 4 of them. Quadrantal just means the one that are lying on the boundary. So 0 degrees is quadrantal because it's on the x-axis. 90 degrees is quadrantal because it's on the y-axis. Blah 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 blah. So 270. Where's 270? Start at 0. Where's 270? Yeah, straight down. 270 is this guy on the y-axis. Quadrantal. So that word doesn't mean shit. Who cares? Can somebody give me one positive angle that's coterminal with 270? How would you get it?
630.
Huh?
630
How'd you get that?
plus 360.
Yeah, plus 360. How would you get another positive angle? When you just add 360 again. Now, if you feel really creative, you can add 3600. Right? You can add 3960. Any multiple of 360 is just how many times you freaking turn around. You guys with me? How do I get negative ones? Subtract 360 as many times as you want to, right? So this is key. This is huge. You guys all already know what a sine wave looks like, even if you don't know what sine is. Sine wave, what's it look like? Tell me, if anybody's watched any horror movies, they always have an oscilloscope somewhere that's doing this thing, right? Here's a sine wave. Whee! Do you see how it repeats forever?
It's the same, it's the same.
Because it's kind of taking elements of a circle. And what does a circle do? Circle just keeps repeating forever. I'm here. I'm here again. I'm here again. All right. So graphs that come from circles should be repetitive. Because circles are freaking repetitive. How do I get to this point? Well, you can rotate by this much. Or you can rotate by 360 more. You can rotate by 360 less. And you get the same place. That's all this stuff is saying. Is that okay? I love it. And by the way, don't take my tone to mean you should know this. It's just, I'm trying to show you it's not as difficult as some of the wording makes it sound. Coterminal just means add or subtract rotations. Because you'll end up at the same exact place. Okay. Is that cool? Or maybe not cool, but okay. Alright. Anything else, guys? And I really want to make sure about something. Shoot, I think I gave all my homework sheets away. Yeah, homework for this, be careful. Notice where it says E30, E40, E50. Don't do every single homework problem unless I say to do all of them. E30 means every third one, E40 means every fourth one, right? So I still have people that turn in homework and it's like, they do every problem. Lots of good practice there, but holy shit. I'm sure you don't have time for that. Okay. All right, so let's get into some new stuff. Not really new because you've seen this before, but new to us right now. So what does the Pythagorean theorem, what does it say? Yeah. A squared plus B squared equals C squared. What the shit does that mean? What kind of triangle does that work for?
Right triangle.
Right triangle. I love it. So Pythagorean theorem. So if I give you a length of 3 and a length of 4, if I just lay them end to end, it would be 7, correct?
Yes.
So if I took this 3 and I laid it right next to this 4 and I put a little piece of gum there or something so it would be 7 long, yes?
Yes.
If I rotate this up, isn't this side, how does that side relate to 7? Considering straight down was 7, if I rotate that side up a little bit, is this side bigger or less than 7?
Bigger. Less. Less.
Totally less.
Yeah, way less.
You guys all with me? So if I lay this down, I almost got this right. If I lay this down, that's 7 straight out, right?
Mm-hmm.
If I pick this up, isn't this side getting closer to that?
Yeah.
Yeah, so it's going to be a little less than 7.
Yeah.
If I really, now watch this. If I take that side and I rotate it all the way to here, all right. Now, well, maybe not there. Is that side more or less than 7? Way less. Okay, good.
Yeah.
Right. So the more I kind of turn it, the smaller that remaining side is. If I turn it so that it exactly makes a right angle here, pretend like that does. And I heard the answer already. How would I figure out how long that side would be?
3 squared plus.
So some of you guys know some of these triangles already. So there's a 3, 4, 5 triangle. Do you guys know 5, 12?
13.
5,
Oh, there it is. Right. There's a 7, 24, 25. There's a ton of them, right? Those are all called, believe it or not, Pythagorean triples. Ooh. So if I just gave you some arbitrary triangle, it's probably going to have gross sides, right? If I just made up some arbitrary lengths. How do you get the length again? I'm sorry?
3 squared plus 4 squared and squared root.
We'll call this C for now. Right, what's 3 squared?
9.
16, so 25. And what squared is 25?
5.
We're assuming it's positive because we want, like a real triangle that exists. Triangle's got a negative side. Like, what? Okay. That's why I love it in algebra when a student tells me to build a shed, you need negative 8 feet on this side. I'm like, okay. If you build that, I don't know if I want to come see that. From very far away, maybe. I don't want to get close to it. Anyway, sorry. So a very quick visual. There are 50 proofs of Pythagorean theorem that I am aware of. I don't think I could do them all right now, but there are way more than that in existence. One of our presidents actually kind of played around with making new theorems. It's weird. It's one of the Roosevelts. I don't remember which one. We had a couple Roosevelts. Help me out. Let's say this is A, let's say this is B, let's say this is C. Good? Amazing, Jeff. Normally, it's standard practice to make the side opposite the hypotenuse C, right? If I make a square right here, if it's a square, what's the length of this side? And what's the area?
A squared.
A squared.
If I make a square here, what's the length of this side?
B.
B. What's the area? Pretend like that's a square. Holy crap, and a half, Jeff. Poor little dude. Oh, God. Pretend like that's a square. What's the length of this side? C. What's the area?
Squared.
There's a really cool video that you can look up, but it's got this guy, he constructed this thing with water, and these are full of water, and then he turns it around, and the water flows right into there and perfectly fills it up. So Pythagorean theorem, one way to remember it is this square's area plus that square's area equals that square's area. And that's the idea, right? And this is not even really a proof, but it is a nice visual to remember it. You guys already know Pythagorean theorem, though you should, but just to help in case you're not really too aware. So really quickly, can you guys, without saying anything, figure out what this is? Pretend like that's a right triangle. It's been out in the sun for a while. Poor little dude. So the formula, of course, is a squared plus b squared equals c squared. The most important side is the hypotenuse. How long is the hypotenuse in that?
3. Oh, no, 11.
11. Yeah. Hypotenuse is the side that is across from the right angle. And the way I like to think of it is any side that is across from the biggest angle, that's the biggest mouth. So you can put the biggest stick in it. And being the nerd I am, I always think about when Luke is fighting the Rancor and he puts the stick in the guy's mouth. So he needs a bigger stick if he's got a bigger mouth. Right? No, if you've never seen it, you're fine. Big mouth, big stick. Small mouth, small stick, right? How do you figure out this side? How do you set up the equation?
B squared plus.
Yeah, so what is C? What is C?
121.
C is 11, so, okay, I'm going to catch up to you. Does it matter if you call that A or B?
No.
Nope. It doesn't matter, we'll call it A. So 3 squared plus B squared, so we'll say that we're looking for B. Okay. 11 squared is? 121. Subtract 9. So B squared equals 112. B is what? Square root of 112. Now, if you throw that in your calculator, will you get an exact answer?
No.
Hell no. Our brain sees decimals and goes, oh, that's exact. No brain. It can never be exact because you stop it. Can anybody simplify that, though? That is simplifiable. Yes, it is. It is totally simplifiable. It's like me, I'm certifiable. Simplifiable because, did I talk to you guys about, remind me if I talked to you about this. How do you tell if a number is divisible by 9? Does anyone know, for example? If the numbers add up to a multiple of 9, right? So 54 is divisible by 9 because 5 plus 4 is 9. Multiple of 9. 99 is divisible by 9 because 9 plus 9 is 18. Multiple of 9.
63 is divisible by 9.
We got 6 plus 3 is 9. Okay. The rule for 4, how do you tell if a number is divisible by 4, is if the last 2 digits are divisible by 4. Why is that? Because 4 goes into 100. So of course 4 goes into 101. multiple of 4, right? Do you see what I'm saying at all?
Yeah.
Do you have to know this? No. Should you know this? Yeah. Is it your fault? No. Nobody might have ever told you. Why is 4 special here?
2 rad.
Because I can square root 4, yes? All right, so help me out. 4 goes into 100 how many times?
25.
25. 4 goes into 12 how many times? So 4 goes into 112, 28 times. Now what's really neat is 28. What's 28? 7 times 4. So this is actually, is everybody cool with this? This is 16 times 7. 4 times 4 times 7. So what's the square root of 16?
4.
What's the square root of 7? I don't know. So that's what the answer is. That's the exact simplified answer. Is that all right? Huh?
That's good to know.
Yeah, it is. So, very quick side note. Did anyone ever heard of that 9 thing before?
Yeah.
I don't care what the number is. All right, I'm going to have to be careful about this now. Shit. All right, let me see. I think that one. All right. Does it? So this would be 6, 8, 15, 24, 28, 31, 36. Is that a multiple of 9?
Yes.
So this is divisible by 9.
Yeah.
It's also divisible by 3. 3's got the same rule. If you add them up and it's a multiple of 3, it's divisible by 3. Now I know we all have calculators, but as humans, isn't that good shit to know?
Yes.
We all made this shit up, right? All the number shit is made up. Do you guys understand? The symbol for 2, the fact that it's based on 10, it's all shit we just chose. Yes? We should kind of know some of this. I'm sorry. The 4 one is nice. The last 2 digits. So if I just do this, you can do it, Jeff. There you go, buddy. Is that number divisible by 4?
Yeah.
Yeah, because the last 2 digits are divisible by 4. All right. If you're not interested in this at all, okay, but you're fine. You can live life without knowing this, I guess. Okay, so that's one thing. Pythagorean theorems. You're going to see some of that in the homework, and you're going to see Pythagorean theorem ideas this entire semester. Yes.
So, the last math class I took, we also kind of did like we were working on the Pythagorean theorem. Like if you have the hypotenuse and one of the sides, you can do c squared plus c
Oh,
squared.
what did I just do? Okay, I did it right. Good.
Yeah. you
Part of
can
my
do
brain was like, did I set that up
You
right?
can do c squared equals b squared minus a squared. too.
Well, you can do, in this case, I could have done this. I could have done b squared equals c squared minus a squared, right?
Yes, that as well.
Yeah, which is what we eventually did, correct?
Yeah.
Yeah. Exactly right. You can kind of modify the equation from the beginning, or you can use it directly and then solve.
Yeah.
Either way, I love it. Okay, all right. Nothing too ground shaking there. Now, something else that will come up is the distance formula. So, oh my gosh, I just need one giant eraser. Raw. Like an Etch-a-Sketch idea, just shake the board. All right. If I have 2 points, say I have the point, all right, let's start off nice. If I have the point 1, 1, and let's just say this. Let's start off with something really nice. How far apart are those points? That's crazy. Why is it not always that easy? Because how far apart are those points? Are those 2 apart?
No.
Aren't they a little more than 2 apart? Because now not only to get there do I have to walk over, I have to walk up. If I do as the crow flies, it's going to be a little longer than 2. Is everybody cool with that?
Square root of 2.
Didn't I just make a triangle? Do you guys see a triangle I made?
Yeah.
What if these are roads? Anybody ever been to Salt Lake City?
Yeah.
Salt Lake City is almost, it was almost too much for me how freaking perfectly grid-like all the streets were. I don't know if you understand what I'm saying. Stupid perfect. I'm from Virginia Beach. I used to live in Virginia, where a road would intersect with itself. You understand? That would blow the minds of anybody from Salt Lake City. So if I wanted to go to this point, I would go over 2f1, right? Like a slope idea, but I'm not asking for the slope. So isn't there a triangle here?
Yeah.
And I'm asking for what that is? Isn't that Pythagorean theorem?
Yeah.
All right, how long is this side? 2. How long is that side? 1. So how do you figure out that side? Sorry, you said it perfectly, and I said drunk. Oh boy, 2 strikes, Jeff. All right. So this would be 2 squared plus 1 squared equals c squared, right? In this case, let me call it d for distance. Yeah. There we go, buddy. So then d squared equals 4 plus 1, 5. So the distance would be square root of 5. If you give me a decimal, that's not exact, right? Now, if you were telling me how far away you live, I don't know anyone that would say, I'm about square root of 5 miles away. So if this was a word problem, like how far does Mark have to go, it's fine to make it into a rounded decimal. It's not the exact answer, but it's a freaking real life answer, yes? Okay. So what is this in general? So let's say I just give you 2 points, x1, y1, and x2, y2, and I want to know how far apart they are. I want to know what this is. Can you make the triangle? Sure, right? How long is this side?
We don't know.
Yes, we do. We totally do. You know exactly how long it is. Yeah, it'll be y.
Minus 1.
In this case, it'd be y1 minus y2, but yeah, let me just say y2 minus y1. That's fine. I'm gonna square this shit anyway, who cares, right? Just want to make it look more like the form. How far is this side?
x2 minus x1.
Yeah, x2 minus x1. So then how would you get the distance? Wouldn't it be d squared equals, well, how long is this side?
x2 minus x1 squared plus y2 minus y1 squared square root of.
Doesn't that look a lot more complicated than the Pythagorean theorem? Of course. Because to get what I need for the Pythagorean theorem, I've got to use 2 things. That's why there's places for 2 of them, right? It just looks worse, but it's just the stupid Pythagorean theorem again, right? That's stupid, you're fine. So then if I square root, I get the ultimate. Which makes it look so much worse than what it is. It's just Pythagorean theorem, right? Okay, I like it. Hey, Mikey. Okay, so you're going to see some formulas some problems in the book. They're like, okay, you start at the point this, you go to the point there, how far did you go? Okay, just throw that stuff in there, right? You guys see the part that looks like slope. What would the slope be between these 2 points? Do you remember the slope? M equals?
x2 minus x1 over.
Careful.
I mean y2 minus.
Yeah, y2 minus y1 over
x2 minus
x1, sorry. So it's the rise over run, y's rise rhymes. Rise over run, y's over the other guys. Okay. But we're not talking about slope, you're fine. Okay, just 1 point back. All right, so we are done with review. Everything we've done so far, some of it was further than you've ever gone, but everything should have been stuff you've sort of seen before. So now we're going to get into the actual trig, right? All right, I already saw this. You guys ready? By the way, just so you know, today's going to be, obviously, a lot of days are going to be me talking a lot. So I'm sorry. Next time I am going to have kind of like a group worksheet that we're all going to do, kind of reviewing what we did today, and then we'll do some new stuff. Yes? And then I'll also figure out when the first quiz is going to be. So we'll talk more about that next time. Trigonometry. Trigonometry is a study of angles and how they relate to lengths. And the way that we build them, this is really, really silly how we build these things. And then the amount of uses we get out of them is insane. So, for example, my little brother, real quick story, my little brother hated math. So like just hated math, just didn't get it. And then later in life, he was shadowing a surveyor, thinking about going into that. And he's like, a trig makes sense now, Jeff. So have you ever seen, you know what surveying is? Right? I don't mean talking to people getting their, well, who do you think? Who are you going to vote for? No, like they set up the tripod things, they look through the lawn, they look at somebody else, and they're trying to see how much is the land shifted and so forth. It's all about freaking angles. All about angles. Right? But they shortcut the work. Just like any, if you go into engineering, if you go into computer science, any math stuff, you kind of make it specific. Right? So he understood it because now it was less conceptual, it was more very specific. Right? So all trigonometry is, at the heart of it, is ratios of sides of right triangles. Right? So let's write them down. It's ratios of sides of right triangles. That's all it is. So what's a right triangle we were just working with that we know all the sides? We were just working with it. 3,
4, 5.
4, 5. I love it. Let's call this angle theta. I already talked about theta, right?
Mm-hmm.
Okay. It's going to be a letter we see a lot. We're also going to see A, B, C for angles. We're going to see alpha, beta for angles. Theta is like X. Theta is like the main one. There's a function, so we're going to define a trig function for every possible ratio of sides we can make. What do I mean by that? For example, the ratio 3 to 5.
Sign.
That is a ratio I can make, correct? So I'm going to assign that the sine function. And you guys remember logarithms?
Mm-hmm.
Don't freak out. Don't freak out. Everybody stays. The worst thing about logs, the thing that really trips students up, is it's the only function you've ever seen where the function symbol is a word. Log, right? Normally it's a simple square, root, square, you know, but log, and you're like, oh. So unfortunately, if you didn't like that, we're going to continue that. So, sine theta. For any right triangle, all the sine is a ratio of the y side to the hypotenuse. And we're going to call that hypotenuse, we're going to call it r. I don't know if you guys know why. So a big thing that's going to come up later is called a unit circle. And the reason it's called a unit circle is because it has a radius of 1. So instead of a hypotenuse, we're going to call, instead of h, we're going to call it r, just to be consistent. R. Okay, I like it. You guys all with me? It doesn't matter what letter we use. It really doesn't. But eventually it's going to relate to a radius. So we just chose to call it r instead of c, instead of h. So for this specific triangle, what's the sign?
3/5.
Yeah, 3/5. I like it. What is always the largest side in a right triangle? Always. Hypotenuse. What is always on the bottom of a sign? What is the sign defined to have on the bottom? The hypotenuse. You guys all with me? So think about this. Can the sign ever be bigger than 1? Because what's true? That's the biggest side, correct? And I'm taking this side divided by that side. The biggest that could be, somehow, we're going to talk about it later, is 1. I like it. Maybe. Okay. Survey with me so far. Nothing to read. So I want to point something out. If I made this triangle twice as big as it is now, would the angle that I'm looking at there change?
No.
Of course not, right? One of the first things we talked about was the rays, and I don't care how far they go, the stupid angle stays the same. Angle didn't care. It's immediately defined, and then these guys can go as far as they want to, and the angle doesn't give a shit. So if I made this twice as big, I'm telling you that's twice as big, how long would this side be?
8.
How long would this side be?
6.
And how long would this side be? 10. what would the sign then be? Well, let's go one step at a time. So what would it be? It would be 6 over 10, which is 3/5. So every possible angle I can put in there has a specific value for sine. Let me say this again. Whatever angle I make this does not matter how big the triangle is. It's always going to have the exact same value for the sine of it. It's always going to reduce to the exact same thing. Because however big the triangle is, it's just multiples, and the multiples cancel when I set up the ratio. Does that make sense? Later this semester, we're going to be able to do stuff like, what is the sine of 60 degrees? It doesn't matter what triangle it lives in, because it's one number. Sine of 60 degrees is a number, because no matter how, if you put a 60-degree angle and you make the triangle bigger, it's going to reduce to the same damn number. Okay, maybe. Which is why, I don't know if any of you have looked at your calculator and seen there's a sine button. If you hit sine of 60, it will give you a number. It doesn't care what the triangle is, because the triangle will always reduce to the same number. Maybe. All right, this is more than you have to know right now, but I'm just getting you ready. All right, so another thing is, poor little purple dude's dying. Remarkably enough, there's a cosine, and its symbol, because math people are very creative, is cos. And it is defined to be the x side over the hypotenuse. So by the way, real quick, I want to identify this. I will talk this much, including what I'm about to say, about this idea. There's an idea called SOHCAHTOA. Has anyone ever heard of SOHCAHTOA? All right. If you really love it, that's fantastic. Continue using it. I wish we never taught the damn thing. It will only help you out this much. If you remember that sine likes y, cosine likes x. That will take you through all the way up to the highest freaking class I teach you. That idea is consistent. SOHCAHTOA doesn't give you shit. It gives you one thing and that's it. No, I don't want to shit on it. It's fine. But it's just, I just wish we never taught it. It's so unnecessary. What is the cosine of this triangle and this angle? Sorry.
4/5.
This angle in this triangle, the cosine is 4/5. I love it. Okay. And there's a third primary trig function. What's the last ratio that we haven't created anything out of yet?
Y over x.
Yeah, we haven't done these guys, right? We did everything with the hypotenuse, we just haven't done these guys together. So there's 6 total trig functions, 3 of them are the main ones. So the other one is called the tangent function. And the definition of the tangent is exactly what you just said. It's y over x. So for this specific triangle, what would it be?
3/4.
Yeah, 3/4. So I really want you to understand, the triangle is not what is actually really important. Because I could double it, I could cut it in half, I could make any triangle that has that angle in it, and it will always reduce down to whatever I just got. Does that make sense? If I make this 3 times as big, the 3's will cancel, it'll come back to 3/4. So we talk about trig functions evaluated of angles. Just having them live in a triangle makes it easier to kind of work with immediately, right? Okay, maybe. But for example, 45 degrees. There is a sine of 45 degrees. The 45 does not have to live in a triangle. It just has to be an angle. That's all. The triangle just kind of gives me a nice visual, concrete numbers, but sine of 45 degrees is a number. It exists by itself. We'll get there eventually. Okay, how you guys doing so far? I really, really want you to understand that's silly. That's silly. Just put a number over another number. There's a trig function. So on one level, it's kind of like, all right, what good is that? Yay, go math. You put numbers over numbers. But on the other side, it's stupid how much stuff we could do with this. It's crazy. All right, okay. So for example, wouldn't you like to know what the angle is? Wouldn't that be a good thing to know? I would like to know what the hell that angle is. Can anyone tell me? Let me just see. Is it bigger or smaller than 45 degrees? If it was exactly 45 degrees, what would have to be true about these two sides? They'd have to be the same.
Yeah.
Because if that was 45 degrees, then that is 45 degrees. Same mouth, same size stick to put in the mouth, right? Okay, maybe. So that's 3. So is that bigger or smaller than 45 degrees? Smaller. It's got a smaller mouth because it's only got a stick of 3 in there, right? What is it exactly? We'll find out. We don't know yet. Okay. Yes.
So it has to be smaller because it's 3, but.
Yep.
If it was like exact or. So you're saying if it's exact, what do you mean? Like,
Exact. I mean,
So.
if it was 45 degrees, these would have to be the same size. Because this would also be 45 degrees. Same size mouth, same size stick in the mouth. Right, and I don't know if you guys like the stick in the mouth thing. I think you'll see later when we're doing something called solving triangles. The stick in the mouth thing is going to be really useful. All right, you'll see. Yeah.
So for sine, cosine, and tangent, the y and the x, is it always determined just like imagining the x and the y axis? Or
Yes, but
I'm just
one
trying to determine
thing,
how we
the
assign those.
The one thing SOHCAHTOA has is it doesn't matter where the angle is. Where's the angle in my triangle right now? Let me tell you, is it in the base or not? What do you guys think? Is this in the base of the triangle or not in the base of the triangle? This is in the base, correct? So the only time that these really work is if that angle is in the base. If the angle I was talking about was over here, and let's use a different symbol. Let's use alpha. All I would have to do is this. If I want to know what the sine of alpha is, I just have to do this. Now what's the y side? This. So it'll be 4/5. So when does this definition work? When the angle is in the base. Real quick thing about SOHCAHTOA. Who has never heard of SOHCAHTOA until I just said it? Okay. I almost feel like not talking about it at all, but people love it. I don't blame you. But again, it's a crutch and it doesn't help you get very far. It helps you get this far and then it goes, all right. If you just remember sine likes y, cosine likes x, that takes you every freaking where. It takes you through Calc 3 and beyond, through physics, it takes you everywhere. SOHCAHTOA, if I'm looking at this angle, isn't this the side opposite from the angle? So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. TOA, tangent, is opposite over adjacent. Okay. So if you already know SOHCAHTOA, okay, if you don't already know it, I highly recommend you don't use it, to be honest. So real quick, let me show you. This is on the handout I'm going to give you next time. Has everybody got the sine, cosine, tangent? Okay. We'll talk about the other 3 in a minute. The other 3 are kind of silly, but you'll see why. So if I had this triangle, and I'll just give us a nice angle A. What do you got, Jeff? Do you remember anything? No. Oh yeah, let's just do this. Okay, let's just make it nice. And I want to know what the sine of A is. Is my angle in the base?
No.
So how do I take care of that? Or turn the paper, right? So what's the y-axis then? 12, right? So this is y, this is x, this is hypotenuse with all the rings. So what's the sine then? 12 13. Sine likes y. 12 13.
I keep trying to understand what you say when you flip it. Do you mind like drawing it for
sure.
me?
So if I just redraw it, or if it's on your paper, you can just turn the paper. But if I just redraw this, here's A, here's 5, here's 12, here's 13. Angles in the base now, right?
Cool.
So the side that
Understood.
looks like y is y. That's all.
Cool.
That is
Awesome.
the
makes
one
sense.
thing SOHCAHTOA does better. Is
That
it-
makes complete sense. You're making that side the base because you're.
Yes.
Cool. That
So
makes
if
sense
your
now.
angle is in the base, that definition sine likes y works. But but remember, do trig functions have to relate to an actual triangle? No. So SOHCAHTOA helps if you have an actual physical triangle. Do you always have that? No. So that's why I'm trying to get you guys sine likes y, cosine likes x. It's going to help a stupid amount if you just remember that. Just remember the angle's got to be the base. Yes?
When you're saying base of the triangle, do you mean like in between x and y?
Can you tell me what's the base, how long is the base of this triangle? How long is the base of this triangle? 12. Is the angle in the base? No. So if I turn it, now what's the base of the triangle? 5. Is the
so-
angle in the base?
Okay, so the bottom.
Yes. That's what I mean. I love it, I love it, I love it. I like it a lot. Okay, alright. So if you want to keep using your SOHCAHTOA and you're like, this guy sucks, whatever, fine, you go for it. And later you'll say, oh shit, that's what, okay. So the other three trig functions, the other three trig functions have to do with these guys' reciprocals. Because we've made all the possible ratios we possibly can, right? Because we haven't left any sides out. The only thing we can do next is flip them. So on one level, that's like, way to go. But they're still useful, right? So if I flip sine, if I do 1 divided by the sine, we call that function cosecant. So always remember S goes to C, C goes to S, you'll see in a minute. So this is the cosecant. Let me write the symbol, and above it I'll write cosecant. So what would that be? It's 1 over sine, so the cosecant is?
R over y.
R over y. If I do 1 over cosine, I get secant. So that's going to be r over x. Is that cool? By the way, if you ever take calculus, you will definitely see why this is secant and that's cosecant, right? Right now it might not make a lot of sense. It seems like if that's sine, this should be cosine, because they're related to each other, but that actually makes no sense if you go any further in mathematics. Right now we're just sort of like, this is how we're defining it. Tangent, this is the one that makes sense, because it actually works later too. 1 over tangent, what do you think that's called?
Cotangent.
Holy shit. Cotangent. Sorry. And that would be? X over y. Okay. So an example problem I would give you, I would say, given this triangle, find all 6 trig values for B. So do it. And of course you're missing something to be able to do it, right? Yes.
Sorry, I'm just having a little trouble reading that. What are the letters for cosecant?
Where are we at here? Cosecant? CSC? Yeah, sorry. Let me see, is it better or worse if I crank the lights all the way up? I'm worried about the glare. Better or worse? Oh, the same? Okay. Oh, that's actually good. Yeah, okay. So of course, you could get 2 trig functions right now without any work. What trig functions could you get right now, no work?
Cotangent, tangent.
Cotangent and tangent, right? So what's the tangent of B?
5, 7.
Good. And what's the cotangent of B?
7 fifths.
7. Now what do you need to be able to get any of the other 4?
The hypotenuse.
You need hypotenuse. What do you have to use to get that?
Pythagorean theorem.
Pythagorean theorem. So it'd be 25 plus 49, 64,
Which is 8.
40, wait, 25 plus 49 is 74.
74.
Yeah, yeah, there you go. And I don't think that'll reduce, that won't simplify, because 74 is 2 times 37. There's no square number in it. You guys see that? You have to check though. You have to simplify it if you can. But that won't simplify. So help me out, what's the sign of the...
5 over
Yeah.
74.
Now, real quick. Does anyone remember that why that is not a good place to stop?
Because rad can't be on the bottom.
Yeah, radicals suck already. And again, I don't really believe that. I think radicals are awesome. But radicals suck already. So if I'm dividing by them, I'm saying, what the shit? So we almost always rationalize that. Does that sound familiar to anybody? The bottom is currently not a rational number. It is irrational. We need some help, right? How do I rationalize this dude? Multiply by the square root of 74, yeah. So the reason I cannot do that is because I only have one 74 in there. Let me give it another 74 and then I can do it. So the top looks worse, but the bottom looks great. What's square root of 74 times square root of 74?
74.
74, right? Half of 74 times the other half of 74 makes a whole 74. You guys all, does that look familiar? Have you guys done that before? You're going to do that a lot. A lot, yes.
Would you have to do it on the other side? Like,
Other side, what do you mean?
Would you also have to multiply sine b by rad?
No, no. Nope. In fact, I'll multiply the other side by exactly what I multiplied this side by. Times 1. Done. Because didn't I multiply by 1? Cool. So I didn't change the number, I just made it look different. If you put this in the calculator, you get the exact same thing if you put this in the calculator. Exactly the same.
So, how's tangent of b 5 over 7 cotangent?
What's tangent defined to be? What side over what side? What's tangent defined to be?
Y over x.
Y over x. What's the y side? Because the angle's in the base, correct?
Right.
What's the y side?
Oh.
5. So, oh, yeah, so somebody asked about x, y axis. This is exactly, once the angle's in the base, x axis, y axis. I love it. SOHCAHTOA would work. But again, sometimes teachers teach 170 and they don't teach beyond 170. Like, that could happen. Like, I was a part-time teacher, you just get whatever the shit's left over. And sometimes all that's left over is like, 170 and nothing above that. So you don't think about where students have to go after 170. SOHCAHTOA would be good right now. It would. I will admit that. But it will only help you this much. If you're going any further in mathematics, it will very quickly not help you anymore. If you remember, put that in the base, sine likes y, cosine likes x, you're golden. In this class, you'll see why. You'll see why it's better. And time flies. What about cosine?
7 rad 74 over 7.
Yeah, so 7 over rad 74, right? Because it likes x. So if I multiply top and bottom by rad 74, I get this business, right? Tangent, we already did. What about cosecant? Real quick, cosecant. I don't want to flip this over.
No.
Because look at this. If I flip this over, what do I get?
Square root of 74 over 5.
Which
Which is good.
I'm done with it. Right? If I flip this over, I'm going to have a rad in the bottom. It's going to suck big time. So I'd much rather just flip it the way it was to begin with. Become a 4. And of course, secant would be
Rad 74 over 7.
rad 74 over 7. I love it. So right now, I would love it if you're like, well, this is kind of boring. You just put, and that's very weird to hear a math teacher say, I really hope you find this boring. But on one level, it kind of is. That's all a trig function is. Just go this over this side over this side, this side over this. That's what it is right now. It's insane the number of things you could do once you've got this defined. It is absolutely crazy, the number of things you could do. So right now, it's like it doesn't seem like this is gonna go much anywhere, and I don't blame you if you feel that way. Let me see, did I forget anything? No, good. So, let's see, real quick. I'm gonna erase all this, you ready? So, let's say I've got a triangle. Yeah. I'm not gonna tell you what the sides are. What is sine theta? Oh, Jeff and a half. I love this shit. Let's like do that. I didn't mean to add an extra layer of, oh boy. What's sine theta?
Y over R.
Y over R, okay, that's crazy. What's cosine theta? That's crazy sauce. What is sine squared? Yeah, y squared over r squared, is that cool?
Yeah.
Okay, what's cosine squared?
X squared over Y squared.
X squared over r squared. Right, you guys with me? Do those have the same denominator?
Yeah.
So you get x squared plus y squared over r squared. But what is x squared plus y squared? So what's x squared plus y squared?
R squared.
R squared, right? Pythagorean theorem, right? So isn't this r squared over r squared? Which is 1? Does that matter? How many triangles did I just draw up here? I draw an infinite number of triangles, do you understand? I just drew an infinite number of triangles, because what is y? What is x? Whatever the shit I want it to be. Yes? As long as r is x squared plus y squared square root. Yes? So I just drew an infinite number of triangles. So does it matter what angle is in this equation? The answer will always be 1. This is a, let's try grammar, Jeff. This is an identity. This is our first of many. Oh boy, Jeff. Make it seem really creepy. There will be many identities. You won't know who you are anymore. No. So this is our first identity, and not surprisingly, this is called the Pythagorean identity. This is one of 3 Pythagorean identities. Why do you think we call it the Pythagorean identity?
It will always be the same.
This side likes sine likes y, cosine likes x, right? So this squared plus that squared is equal to r squared over r squared is 1. It just comes right from the Pythagorean theorem. It's because sine is like y and cosine is like x. So of course when you square them and add them, you're going to get r squared over r squared. You're going to get 1. Maybe. Now why are there 3 of these suckers? I don't know. Oh yeah. So, you see, make sure I'm not skipping something. No, I'm not. Good. Okay. Watch this. Last thing for today, and then we'll leave just about right on time. Can everybody please just take a moment, divide both sides, divide each thing by cosine squared. Because I'm crazy, just deal with that fact, right? I am insane. Divide each piece by cosine squared. Do it. Oh, some big guys are like, I don't want to do it, Jeff. Maybe. It's fine if you don't want to, fine. So what do I mean? I mean divide each piece by cosine squared. I'll do this one. Okay. What is sine over cosine? Well, let's think about that. What is sine divided by cosine? Well, let's see. What do we get when you do sine divided by cosine? What do you get? Yeah, the r, these cancel, yes?
Yeah.
Y over x is tangent. So sine squared divided by cosine squared is tangent squared. What's 1 over cosine? S goes to C, C goes to S. What's 1 over cosine? Secant. So 1 over cosine squared is secant squared theta. There is the second Pythagorean identity. you see how that's just built from this one? So you're going to have to memorize several identities, and I will not make you memorize other ones. I basically make you memorize every identity that I have memorized. And I will tell you exactly. I'll give you, once we talk about all the identities, I'll give you a chart that's got all of them up there, and these you got to memorize, and these you don't. So you know exactly what you're responsible for. I'm sorry. Yes?
So are these identities supposed to like help us out later on?
They are insanely useful. If I know that sine theta is 7/11, I can plug it in here and solve for cosine theta. I don't even need to draw the triangle, right? You see what I mean? I don't have to find the other side. It'll just work out.
Is this identity stuff going to be like on this upcoming homework?
Yes.
Okay.
It was we just now, just so you know, we basically finished 1/4 just now. If you take this and divide by sine squared, last thing I promise. Did you understand that, Jeff? Sine is 1. Cosine over sine is cotangent, because that's the flip of the tangent. 1 over sine squared is cosecant squared. I want to point out, do you see how this equation has nothing but co-shit in it? And this equation has no co-shit in it. That's the first inclination about why we called some things co and some things not co. Do you kind of see what I'm saying? Not yet, Jeff. Okay. All right, that's enough. That's enough for today. All right, so Wednesday we'll talk about when our quiz will be, the first quiz, and I'll have that group worksheet to give you. Okay, I'll see you guys.